Okay, so my task today is to show you the map of the complexity landscape of fixed parameter directed Steiner network problems and how we obtained this map. And for this, let me start you off with a definition of the undirected Steiner tree problem. Okay, so we have an undirected edge-weighted graph and a terminal set, which is a subset of the vertices. You can see them as these purple boxes here. And the task now is to find a minimum cost subgraph that connects all the terminals with each other. Okay, and now note that the problem definition doesn't say anything about trees, but it's an easy observation that because we're aiming for a min-cost solution, that we won't have any cycles in the solution, and therefore the optimal solution will always be a tree. Okay, so this is a point I will get back to in a minute. Before that, let's look at what's known for this problem. So we know it's APX hard, and we know that we can obtain constant approximations. For this talk, I'm not so much interested in approximation, but instead in fixed parameter tractability, where we want to compute the optimum solution, but we allow sort of only a mild exponential running time by saying that, well, the input comes with some sort of parameter, which we somehow usually assume is maybe small, hopefully small, and then we allow running times of the following form. So f for some function f independent of the input size, f of p times a polynomial in the input size n. Okay, in particular, what's not allowed is a running time of this form, n to the p, which would be called an XP algorithm. And for this talk, the only parameter I'm interested in is the number of terminals, which are called k. For this parameter, it's known since the 70s already that the problem is FPT, and the best running time up to date we can get is 2 to the k poly n. So now let's try to generalize this problem to the directed case. Okay, and there are several ways how to do that. The first attempt sort of guarantees that the topology of the solution is the same, so it's going to be a tree. So here, we now have a directed edge-weighted graph, and we have a specific designated terminal called the root, so this guy here. And now we want to find a minimum cost subgraph such that for every terminal there is a path from the root to that terminal. Okay, and it's not too hard to observe that the solution using this problem definition will be an arborescence, so it has a tree structure. Now, approximation-wise, this problem is a lot harder to approximate than the undirected case. However, in the FPT world, nothing much changes. We can use the same techniques as before, which are based on dynamic programming, to get 2 to k poly n algorithm. And now, note that in the undirected case, what we actually wanted to do is to connect all the terminals to each other, which here is not necessarily the case, because only the root is guaranteed to be connected to each other terminal, right? So a different way to generalize the undirected Steiner tree problem is to say that, okay, for every terminal pair, I want a path in one direction, but also in the other direction. This necessarily gives me a strongly connected graph, and therefore the problem then is called the strongly connected Steiner subgraph problem. Okay, where we want to find a minimum cost strongly connected subgraph connecting all the terminals. Okay, and by the way, so the green stuff here is always an example, maybe that was clear, hopefully, of what I'm talking about. Okay, obviously in this case the solution will have cycles, okay, in contrast to before. Approximation-wise, it's sort of, let's say, similarly hard as before for the DST problem. But in the FPT world, something interesting happens now because this problem is actually W1 hard, so we can't really hope for an FPT algorithm. We know, though, that we can get an XP algorithm that runs time n to the k and result by Feldman and rule, where I should point out that this Feldman here is not me, but some other Feldman. Okay, so now our task is basically to figure out, okay, what other generalization of the undirected Steiner tree problem gives us tractable cases, FPT problems, and which ones are W1 hard. Now to do this, I have to talk about demand patterns. Okay, so a demand pattern is just an unweighted directed graph on the terminal set, and it basically tells me how each terminal should be connected to every other terminal. Okay, so for the DST problem, for example, I want the root to be connected to all the other terminals, so the pattern is going to be an out star. Okay, for the SCSS problem, the pattern is going to be some strongly connected graph, so for example, a cycle.
So this means for each vertex to whom he should be connected and who should be connected to him.
So the formal definition follows now. Okay, so I define this problem, the directed Steiner H network problem. H here is a class of patterns. So every class of patterns gives you a different problem. Okay, and so I'm given as input a directed edge-weighted graph, a terminal set, a pattern from this class with terminals with vertex set R. So it has the terminals as the vertices. Okay, and now I want to find a minimum cost subgraph so that for every edge ST of the pattern, in the solution there is a path from S to T. Okay, so here, for example, I have this pattern here, and the green stuff is a solution to this. So for example, I don't know, for this edge here, there is a path from this terminal through here, leading here, okay, etc. For each one of these edges, there will be a path. Okay, so this problem has not been studied much before. There's one special case that has been studied, which is the case when the class H contains every possible pattern. Okay, so if you can get any arbitrary pattern, okay, approximation-wise, it's even harder than before. Obviously, it's going to be W1 hard because it contains the SCSS problem as a special case. And on the positive side, the XP algorithm by Feldman and Rule also works for this more general case. Okay, so so now I have a whole range of problems, and I want to figure out which ones are hard and which ones are FPT. Okay, so I will next go into our main theorem, and then after that I'll talk about the algorithm we got, a little bit about the hardness, and give you some conclusions at the end. Okay. So to give you the main theorem, I need a couple of definitions. First of all, so I want to define a special class of patterns, which I call almost caterpillar graphs. So let's say I take a path on lambda 0 vertices, like here, and now I attach to this path arbitrarily sized outstars. So this would be this picture. Or symmetrically, I can also attach arbitrarily sized instars, as in this picture. Okay, so this I call an out caterpillar, this I call an in caterpillar. And now in addition to that, I want to add a small bounded sized set of additional edges. Okay, such as here. So you can see these purple edges, they can do whatever they want. Okay, but there's only bounded number of them. So formally, I define this class C lambda delta, which contains any pattern graph if this pattern graph has a subset of vertices, edges, f, of size at most delta, so these are the purple edges. And if you remove them from the pattern, then what's left spans a caterpillar, a lambda 0 caterpillar, with lambda 0 at most lambda. Okay, so the so-called spine of the caterpillar has length at most lambda. Okay, there's one more definition I need, which is based on the following observation. So let's say in your pattern you have a path from a terminal S to a terminal T. Then clearly in the solution you will also, in any feasible solution, you will also have a path from S to T, right? So if you add the edge into the pattern, the direct edge between S and T, then this doesn't change the solution space, right? All the solutions are going to be the same. And therefore I define two patterns H and H prime to be transitively equivalent if the transitive closures of those two patterns are isomorphic. Okay, and then the class C star lambda delta just contains all the patterns that are transitively equivalent to almost caterpillars. So now once I have all these definitions, I can give you the main theorem, which is the following. So first I have a technical condition, which is that my class of patterns I'm looking at should be recursively enumerable. Okay, so this will not be so interesting for my talk today, but maybe what's more interesting, so if now I have two constants, lambda and delta, such that my pattern class is a subclass of these almost caterpillars for these two constants, then the problem defined by this class of pattern is FPT for parameter k, and can be solved in this running time here, where tau is some function of the two constants. Okay, and in all other cases, so if these two constants do not exist, then the corresponding problem is W1 hard. Okay, so I get a complete dichotomy of which patterns give me a FPT problem and which ones give me a W1 hard problem. And okay, so just to list a few consequences of our main theorem. So basically, it includes all the known results that that we had before. So DST is FPT, SCSS is W1 hard. We even get the XP algorithm. So for any arbitrary pattern, we can also see from the formulation of the main theorem that we get this an XP algorithm. There is one additional case that I haven't mentioned before, so the so-called Q-root Steiner tree problem, which was introduced very recently by Suchi. So this is a paper appearing at WG. And here, this is a generalization of DST, where instead of only one outstar, I take Q of them for some constant Q. And now I identify all the leaves of these outstars. And additionally, I also introduce a strongly connected graph on the roots of these stars, such as here. Okay. And and we also from our theorem all of these results you have to basically analyze these patterns, and then you can see that for instance here these are special cases, so almost caterpillars, and therefore these problems are FPT. What's also interesting to note is that here, for these two problems, for the two FPT results, we actually even match the running time. For the XP algorithm, it's interesting to note that this gives us an alternative proof, because what Feldman and Rule did is they considered so-called pebble games, and we have a quite different approach where we use more dynamic programming, more in the style of this DST results, the original DST results. Okay, another interesting observation is that, so we know that DST is FPT, so the pattern is sort of quite sparse. I mean, it's an outstar, right? Now, the SSE problem, on the other hand, is W1 hard, and the pattern is somehow strongly connected. So in some sense, it's a much denser pattern. And you might think now that somehow, intuitively, the denser the pattern, the harder the problem. However, this is not the case. So from our theorem, we can also see that if I just take two outstars and connect the roots with an edge, then this is just a caterpillar. So by our theorem, this gives us an FPT problem, a problem that's FPT. But if I remove this edge, then suddenly I get a W1 hard problem. Okay, so we get this weird non-monotonicity here somehow. We can remove edges and make the problem harder. Okay, so good. Yeah, so enough about the main theorem and its consequences. Let's look at the algorithm. So the algorithm is based on analyzing the structure of minimal solutions. Okay, so a minimal solution is one where I cannot remove any edge without making the solution infeasible. And we have two theorems here. So the first one says that, if I have a minimal solution to any arbitrary pattern, then I can measure sort of its complexity, structural complexity, in terms of its number of edges. So in particular, we show that the cut width of the minimal solution is at most 7 times the number of edges in the pattern. And then we generalize this theorem to say that, okay, if the pattern is an almost caterpillar, then we can bound the tree width of the minimal solution by 7 times some term depending on the two constants, lambda and delta. And once we have that, we have sort of a very generic algorithmic result which just says, okay, if I'm guaranteed that the optimum solution to my given pattern has small tree width, so tree width tau, then it can be computed in this running time here. And if you just plug in this tree width bound in this theorem, you get the first part of our main theorem. Okay, so now what I want to do is to give you a brief idea how we obtain this term for the running time. And here, yes, as I said, we rely on dynamic programming. And the main idea is sort of to guess the tree decomposition of the optimum solution. Okay, so since there are n vertices in total and each bag of the tree decomposition contains at most tau vertices, this gives us n to the tau possibilities. And then I also have to guess a subset of terminals which are contained in the subtree of the tree decomposition rooted at the current bag. Okay, so since there are k terminals, I get a factor of 2 to the k due to this. And then the more tricky part is to come up with sort of an encoding, or let's say a pattern, a pattern that encodes the connectivity between terminals and vertices in the bag of my current partial solution. Okay, and it turns out I can get away with something like 2 to some function of the tree width here. And okay, once I have that, okay, so you can already see that multiplying these three numbers gives you the running time. Okay, and how do we compute an entry? Well, here we just rely on the simple observation that a bag of a tree decomposition is a separator. So somehow, you know, if you have a terminal here in one subtree and a terminal in another subtree, then the path connecting them must go through the root bags of these subtrees. And then using the connectivity information we stored, we can put together these partial solutions to give a new partial solution for a specific entry. So that's sort of a rough idea. Okay, so next let's talk more about the structure of minimal solutions. So again, what do we want to do? So we are given an almost caterpillar, okay, and we want to show that the tree width of a minimal solution is bounded. So how do we do that? So what we show is that the minimal solution looks something like this. So it contains a core, and attached to this core is just a bunch of trees. Okay, and so how do we identify the core? So what we're able to do is to find, well, a subgraph of this minimal solution that itself is also a minimal solution to a subpattern of the almost caterpillar graph. Now, what is this subpattern? Well, it contains the spine of the caterpillar, the additional delta edges, okay, and also a bunch of these edges of the outstars, if my caterpillar is an out caterpillar, okay, and but the total number of edges in the subpattern is bounded by this term in lambda and delta. So it's a relatively small subpattern. And now recall that we have this theorem which lets us bound the cut width of any minimal solution for any arbitrary pattern. So in particular, we can bound the cut width of the core in depending on the number of edges here of the subpattern. Okay, and since the cut width also bounds the true width, this bounds the true width of the core. And well, it's a simple observation that attaching a bunch of trees to a graph doesn't increase the tree width. And therefore, the tree width of the minimal solution is actually bounded in the tree width of the core. And yeah, using this bound on the number of edges of the subpattern, we get exactly our theorem about the tree width of minimal solutions to almost caterpillars. Okay, so so much for the algorithm. let's just briefly talk about the hardness results that we have. So the hardness proof proceeds in several steps. The first one is sort of a simplification step. So let's say we have some class of demand patterns. Then we take the closure of this class according to two operations. One being transitive equivalence, so this is the same we saw before, so we can add edges if there's already a path between two terminals. And the other one is identifying terminals. So if you have, so take any two terminals, you can just make them one. Okay, so a little bit like a contraction, but you can also do it if there's no edge between the two terminals. And what we can show is that actually the problem defined by the original class is at least as hard as the problem given by the closure. Okay, so for this we give a parameterized reduction here. And then, okay, then we only work with the closure. This simplifies a few things. So in particular what we can do is we can characterize a closure that is not a subset of class of almost caterpillars, but a set of obstructions. In particular, so this closure will contain all of these type of patterns, or all of these type of patterns, or all of these, or all of these, or all of these. Now what are these patterns? So the first ones here are these pure alpha diamonds. So the first type is you take two outstars with alpha leaves and just identify the leaves. The second one is the same symmetric case for instars. And then we have these flawed alpha diamonds where basically, yeah, you have a pure alpha diamond, but then you have one additional vertex where the edges sort of go in the wrong direction, and the symmetric case. And then you have an alpha cycle, which is a cycle on alpha vertices, so something strongly connected. And then the third step would be to show for each of these types of patterns, this defines a W1 hard problem. So in particular for these alpha cycles, we already know that this defines a hard problem because it's exactly the SCSS problem. Okay? And then we just have to give reductions for each of these four cases. And I mean, if we start out with a pattern class that is not a subset of these almost caterpillars, then the closure, which is an even bigger set, also has this property. And then just going through these steps, we see that the original class defines a hard problem. Good. Yeah, just sort of a rough idea of the hardness result. Let me just give you one concluding remark, which is the following. So we looked at some special cases, in particular planar graphs. So here for the SCSS problem, so recall that for general graphs we have this XP algorithm which runs in time n to the k due to Feldman rule. And for the SCSS problem on planar graphs, actually there's a result here by Hibnis, Hagiagai, and Daniel Marx, who show that you can improve the running time to n to the square root k. Now we also have an alternative proof to this. So recall that we have this theorem which bounds the cut width of any minimal solution. Now we can sort of modify this to show that in planar graphs, the minimal solution has a tree width which is sort of, yeah, which is a square root of the number of edges of the given pattern. And therefore, okay, given our algorithm, this also implies this result here. Okay, so the general algorithm, given the fact that the optimum solution has bounded tree width. Okay, so much for that. So this just basically brings me back to the first slide. So I hope I was able to show you sort of how we obtained this map of this complexity landscape. So, and what was known before our work is basically this part of the map where we had, we knew that the DST problem where the pattern is an outstar is tractable, and we knew that there are some deep waters outside. But now we really have a full map of the world, okay, and we know that there's actually a whole new continent of tractable cases given by these almost caterpillars. Okay, so and that's that's all. So thanks for your attention.